Good. So yeah, you have. So we're going to have this presentation by Jahn on Bruhat intervals, complexes for finite Coxeter groups, and we have 25 minutes, if that's okay. Floor is yours.
Okay, thank you very much for the introduction, and also thanks to the organizers for giving me the opportunity to speak here at FIPSEC. And everything you see today is in joint work with Christian Stump. Okay, let me start by telling you what we are going to do. I first give a little background on Coxeter groups and Bruhat order and fix some notations here. I'll then define the Subword complex and the brick polytope. And then brick polytopes were introduced for spherical Subword complexes, and I tell you a little bit what problems appear if we want to consider them for all types of Subword complexes, and how Bruhat cones appear in this setting. And then we combine Bruhat cones with brick polytopes to define brick polyhedra for Subword complexes. And I'll then show you what statements that were previously known for brick polytopes carry over to brick polyhedra and how we have to adjust them. Okay, we start with Coxeter group, a Coxeter group with simple generators S1 to Sn. This such a group acts as a final real reflection group on an n-dimensional Euclidean vector space, and to this we can associate a root system phi, not necessarily crystallographic. And in such a root system, we can choose a system of simple roots. They will always be denoted by alphas. And non-negative combinations of these simple roots are the positive roots, and so on. And we also need the fundamental weights that will be denoted by omegas. And if you have a simple generator S that acts on omega t for t, another simple generator, then this is given by omega t minus Kronecker delta of S equals t alpha S. A quick example, just to remind you, this is a root system of type A2 for the symmetric group on 3 elements. Here we have the simple root alpha 1, the simple root alpha 2, and on top the positive roots, and these dashed lines are the reflection hyperplanes. And if we draw also the fundamental weights, they lie on these reflection hyperplanes here. And just keep in mind for the rest of the talk, whenever you see a polytope or polyhedron, the directions of edges will coincide with the directions of roots that are drawn in this picture. Okay, for an element in the Coxeter group, we can write this clearly as a product of the generators. And if we have such a product of minimal length, we call this a reduced expression. And the length of this expression also defines the length of the element. And with these words and with a length, we can define 3 partial orders on our group. First one is the left weak order, where we have the cover relation x is left covered by y if there is a simple reflection that we can apply from the left side to x to obtain y, and their lengths differ by 1. This is given a reduced word for x, we can add a letter on the left side to this reduced word to obtain a reduced word for y. Similarly, for the right weak order, the cover relations are given by a simple reflection that is applied from the right side, and we increase in length by 1. This corresponds to adding a letter on the right side of the reduced word. Then third, we have Bruhat order, and we denote this without any letters. So cover relation in Bruhat order is given by is given if we have any reflections. So R is the set of all reflections, not just simple reflections, that we can apply to X from the right side to obtain Y, and we still increase in length by 1. But if we want to describe this via reduced words or reduced expressions, we have to be a little bit careful. Here we have to consider a reduced word for y, and then we can delete a letter at some position to obtain a reduced word for x. In general, it is not possible to extend every reduced expression for x to a reduced expression for y. Two more things before we can come to subword complexes. For an element with a reduced word q1 to ql, we can define the inversion set, and this is obtained by taking for each position the prefix of letters in front of this position and let them act on the simple root corresponding to this position. So if we start with the first position, this is the identity element applied to alpha q1. Then we have q1 applied to alpha q2, q1, q2 applied to alpha q3, and so on. We also need the Demazure product. If we have a word over S not necessarily reduced, then the Demazure product of that word is defined as the unique Bruhat maximal element that has an expression as a subword of Q. You might be more familiar with another definition of the Demazure product, and this is usually given by some kind of greedy algorithm where you go through this word from left to right, and for each generator you can look if you go up in Bruhat order or down, and if you go up you take it for the reduced word, and if you go down you do not take it. A quick example here, if we have a word 1, 1, 2, 2, 1, so this would be generator S1, S1, S2, S2, S1. Then we start with the identity element, look how this acts on the root corresponding to the first letter. This is E applied to alpha 1 is a positive root, so we take this generator for our word. We then look at the next position, 1, have the green prefix applied to alpha 1. This is a negative root, so we throw it away. We would go down in order. Then we have, again, only the green prefix, not the one that we've thrown away. 1 applied to the next root. 1 applied to alpha 2 is a positive root, so we take this one. Then we have 1, 2 applied to alpha 2 is a negative root. We throw the next one away, and so on to, in the end, get 1, 2, 1, so S1, S2, S1, as the Demazure product of the word 1, 1, 2, 2, 1. Okay, now to subword complexes. The input datum to compute the subword complex is a word over S not necessarily reduced. We have here indices of these letters 1 to M, and we have an element that is smaller or equal to the Demazure product of Q in Bruhat order. As I said at the beginning, whenever you see such a relation without letters, this is Bruhat order. And we first take all the subwords of Q that form reduced expressions for our element W. We then take the complements of these subwords. We then write the indices of those complements as sets, and then take the simplicial complex induced by those facets. I'll show you two examples in a second, but a quick remark to the Demazure product in this setting. If we consider the Demazure product algorithm on this word and do not take the reduced word that we get by the algorithm, but the things we throw away, this would lead to a facet in the subword complex for Q, and where the element is the Demazure product of Q. Okay, first example for subword complexes. We have the word 1, 2, 1, 2, 1. This is generator S1, S2, S1, S2, S1. We have the index set 1 to 5, because we have 5 letters. And we take the element W equals 1 to 1 with another reduced expression given by 2, 1, 2. And the facets are these 5 sets that you can see right here. For example, if we have facet I1, we delete position 1 and 2, and what remains is a reduced expression 1 to 1 for our element. Similarly for I2, if we delete the first and the last position, what remains is 2 on 2 is another reduced expression. If we draw this as an abstract simplicial complex, then we have the vertices given by indices, 1, 2, 3, 4, 5, and the facets are just as written here, given by these edges. And I call this example a spherical subword complex because you see this complex forms a one-dimensional sphere. Second example, if we just swap around these two letters at the end, we have the word 1, 2, 1, 1, 2, and we consider another element in this case, W is 1, 2. We then have facets. If we want to search for reduced expressions of this element, we could, for example, take this last 2 here and then have 3 choices for 1. This results in the first 3 facets, I1 to I3. And if we take this 2 at the beginning, we only can take the 1 that is right before that. So this corresponds to the facet I4. And these facets are now 2-dimensional. So if we draw the subword complex, we get these 4 triangles here where the filling is part of the facet. One more thing to say at this picture is that we call this vertex 5 in the facet 3, 4, 5 flippable, because if we would remove it from this facet 3, 4, 5, there is a unique adjacent facet that we can go to, so we can replace this 5 with this 2. This is a flip from 5 to 2. And if we consider this 3 here in the same facet 3, 4, 5, if we would remove this, we get a codimension phase that is 4, 5, and there is no adjacent facet to that. So we call this vertex 3 non-flippable. And now I presented to you 2 examples, the spherical subword complex and non-spherical subword complex. And this is actually a theorem by Knudsen and Miller, who introduced these subword complexes, that subword complexes are spherical if and only if the Demazure product of Q equals the element that we choose. That is what we had in this example. And it is a topological ball, whatever that is, in all other cases. Okay. There are 2 functions that are very important for the combinatorics of subword complexes, the root function and the weight function. And I'll start with the root function here. To each facet of the subword complex and each position, we associate a root. And this is the formula, but I'll explain it at an example. If we have the facet 2, 3, 4 and the index 4, we consider the word, we consider all positions of the word that are in front of this index 4. So this would be the first 3 letters, 1 to 1. We then delete everything that is in our facet. Position 2 and 3 are in our facet, so we delete those, marked in red. We then take the product of these simple generators that remain and let them act on the simple root that corresponds to index 4. In this case, the only remaining thing is the generator as 1, and this acts on alpha 1 because at position 1 we have also position 4 we have also a1. S1 of alpha 1 is minus alpha 1. With this root function, we can define the root configuration of a facet, and this is just the multiset where we collect all root function values for positions in this facet. A quick example for the same facet we just had, that you can see this is truly a multiset. We have for position 2 alpha 1 plus alpha 2, for position 3 and 4 2 copies of minus alpha 1, and we do care about multiplicities. The second important function is the weight function, and this is defined exactly as the root function, but instead of acting on the simple root, we are acting on the corresponding fundamental weight. So you can see here in this example, this is pretty much the same, but in the end we had S1 acting on omega-1, and this is omega-1 minus alpha-1. The weight function is then used to define the brick vector. This is just the sum over all weight function values for all possible positions. And we have a minus sign here in the beginning. And if you're familiar with the topic, we introduce this minus sign in a paper that corresponds to this talk because we can write things in the end a little bit easier with this, but it doesn't change anything on the statements you already know. With a brick vector, we can associate a polytope to the Subword complex, and this is the brick polytope. And it's defined just as the convex hull of all brick vectors of all facets. For the two examples of Subword complexes I've shown you before, we have these two brick polytopes right here. And here, this is the spherical example, and this is the non-spherical example. And you might see that I wrote here root independent and root dependent below this example, so I haven't defined this yet. The Subword complex is called root independent if the root configuration of every facet forms a basis of the ambient vector space. And here you have to believe me that this is the case. And here you have seen that we had a root configuration with 2 copies of alpha-1 of minus alpha-1. So this is not a basis. So here we are root dependent. Okay, I'll quickly talk about some properties of brick polytopes. That's why they're so interesting. And here we only consider the case where the Subword complex is spherical and root independent. And in this case, the vertices of the brick polytope are in one-to-one correspondence with facets of the Subword complex. If you sit in one of those vertices, you can detect the edges that go outwards from this vertex by the root configuration of the corresponding facet. And there's a nice bijection of the elements of the group onto the vertices of the brick polytope. This comes together in several theorems by Pilot and Stumpf from 2015, where they showed that in the spherical and root independent case, the brick polytope is a dual realization of the Subword complex. The local cone over each brick vector coincides with the cone generated by the root configuration. And via this surjection from elements onto the vertices, there is a description on how to obtain the inner normal fan of the brick polytope by gluing together chambers in the Coxeter fan via this surjection. And quick disclaimer again, if you are familiar with the topic, the introduced minus sign had, I had to do some adjustments to these statements because of this minus sign. Okay, brick polytopes were introduced by Pilot and Stumpf for spherical Subword complexes, but what about the other ones? What about non-spherical Subword complexes? And if we take a closer look at the example for the non-spherical Subword complex, I'll explain to you where brick polytopes fail in this scenario. First, what can you see in this picture here? This is the polytope I've shown you before. And in each vertex, these blue arrows are the root configuration of the corresponding facet. So, for example, we have computed the root configuration of this vertex, and here we had 1 copy of alpha-1 plus alpha-2 and 2 copies of minus alpha-1. So these are shown by these blue arrows. If the Subword complex now is not root independent, this corresponds to the appearance of such inner brick vectors. So we lose that every brick vector is a vertex of the brick polytope. And in general, the dimensions do not fit to obtain a realization. If the Subword complex is not spherical, it's even worse. We then have non-flippable vertices, as seen in the example. And these non-flippable vertices correspond to root configuration errors that point outwards of the brick polytope. So these two, for example, would be two non-flippable vertices in the facet that corresponds to this brick vector. Here we have one, and here we have another one. And the last thing to see that this edge that we see right here, this diagonal edge, has no interpretation in terms of Subword complexes at all. So we want to understand non-flippable vertices to see what we can do. And in the case that we have such a non-flippable index in a facet, the root configuration is still a positive root that does not belong to the inversion set. And if you think back on the algorithm of the Demazure product, this means that if we see this by scanning through the word from left to right, we could go up in order. So this is a very unusual situation, showing us that we can insert this generator that now corresponds to our facet into the reduced word of W and obtain a reduced word for an upper cover, in this case, given by R beta W, where R beta is the reflection corresponding to beta. This insertion of letters, or the other way around, deletion yields a connection between those Subword complexes of cover relations. So we fix the word Q and have here W and here the upper cover R beta W. And we can ask a question now, what happens if we consider all of these upper covers that are still below our Demazure product? And this leads to the introduction of Bruhat cones in the context of Subword complexes. And they were first, Bruhat cones were first introduced by Dyer in 1994, I think. And if we have an interval x less or equal to y, we consider an upper cover of x in Bruhat order. Such an upper cover corresponds to a reflection. So there is a reflection R such that Rx equals Z. And this reflection has a corresponding positive root. We then collect for the interval x to y all such roots that correspond to these upper covers. And the Bruhat cone then is simply the cone over these roots. So this is non-negative linear combinations of all roots in this set E+. Quick note here that these roots that we use as generators are actually the extremal rays or just rays of this cone. Okay, please do not try to read anything on this slide. This is just a collection of statements that were previously known by Dyer and that we showed in our paper for Bruhat cones. It's just if you have an interval and you vary something, for example, you consider an upper cover or lower cover of X or an upper cover or lower cover of Y, you get some inclusion properties of Bruhat cones. Okay, back to Subword complexes. Here we have our first great proposition. We can describe the root function values of all non-flippable indices exactly by these sets of root that corresponds to upper covers. And a quick example here where we can see multiple non-flippable directions. If we have Q 1 to 1 and W equals 1, then the set E plus is given by alpha 1 plus alpha 2. You can see this direction here. And alpha 2, you can see this direction here. And if I would consider the cone over this, so the Bruhat cone, this would be this region here. Okay, and what happens now if we combine the brick polytope with the Bruhat cone? The picture looks like this, where combining means, in this case, Minkowski sum. And this looks much better than the picture we had before. in the non-spherical case. So this is exactly what we do. The brick polyhedron now is defined as the convex hull of all brick vectors, taking the Minkowski sum with the Bruhat cone C+ from the interval W to Demazure product of Q. The first important thing is that this reduces to the brick polytope if we are in the spherical case. So here we just get here in the end, we just get a point and we get back our brick polytope. But we have to show that this cone does not destroy the remaining good structure of the non-spherical brick polytope that was still there. And this is given by the following theorem, saying that the Bruhat cone from W to the Demazure product of Q is exactly the intersection of all cones over root configurations. Okay, I want to talk very quickly about the proof of this statement. The forward inclusion is not so bad. Subword complexes can be decomposed into smaller subword complexes, and then you can do some induction on the length of the word Q. And when you put those back together, you have to track what happens to the root configuration and what happens to the Bruhat cone. And this is, for example, a point where we use these inclusion statements that you hopefully did not read some slides ago. The other direction is more difficult. And here we have to, for some reason, if we have given a vertex of the brick polytope, we need to compute the facet who corresponds to that vertex. And this yields an algorithm similar to the Demazure product you've seen in the beginning. And I won't go into any details. This is the algorithm. The idea is the same as before. We go through the word from left to right, and for each generator, we decide whether we want to put it into our facet. This corresponds to the smiley face cases in this picture. Or if we want to throw it away, this corresponds to the skull cases here. And we then have to show, of course, that the algorithm does what we want it to do. If IF is the output set of the algorithm, then we can show this is a facet of the subword complex. In particular, the complement is a reduced word for our element W. So this is a generalization of the Demazure product algorithm in some sense. The functional that was part of the input is non-negative on the root configuration of the facet we computed. This is an essential part in the proof of the statement we want to prove. And we can show that this facet is as anti-greedy as possible. I cannot go into much details here, but just keep in mind, this is also some kind of greedy algorithm. Okay, finally, we can now look at the statements for brick polyhedra that, or for brick polytopes that carry over to brick polyhedra, or how they have to be adjusted. And very quickly here, because I'm running out of time. So we still get the result that the local cone over each brick vector coincides with a cone generated by the root configuration. Now this picture here looks a lot better than it did before. Especially here, we see that this cone generated by the blue arrows corresponds to the local cone of the polytope. We also get a description of how to obtain the inner normal fan, but now we, yes? I can barely hear you.
Yes, I'm just saying you're running out of time completely.
Yes, I have one more slide, I guess, and then I'm done.
Okay.
We have to delete now chambers in the Coxeter fan, for example, these gray chambers here, and then glue some of the remaining chambers together. So here you can see in blue the normal fan of the polytope. And we get an inclusion theorem for brick polytopes, the brick polyhedra that correspond to upper covers. And this leads us right back to the picture of the beginning, where you can see all of these polyhedra for one fixed word, how they include each other. Okay. And then thank you very much for your attention.
Thank you.
So I'm familiar with the motivation for considering these polytopes from cluster algebras. And in that case, they're spherical subword complexes. Can you say something about the motivation for considering these problems for non-spherical subword complexes?
Well, one motivation, if you are familiar with the cluster complexes, might be exactly the picture that you see right here. You can ask, if you consider the intersection of all brick polyhedra that are non-spherical, what is the polytope that you do obtain? And you can see in this picture here that the brick polytope itself, that is the black permutohedron here, is not directly obtained, but we can, the polytope that we do obtain is, in this case, the associahedron. And this is something we are still looking in, so this is not part of the paper, but we think that for the cluster complex example, this is actually an equality. So that the intersection of all lower brick polyhedra gives back the associahedron, the big polytope in this case. So this might be another way of seeing this connection by the intersection of some lower dimensional stuff.
One more question.
I was wondering if the brick polytopes are also generalized permutahedra, and if so, can you say something about the interval when you look at the antipode for the corresponding Hopf algebra or something nice? Something about the interval from that structure.
Oh, I'm not very familiar with Hopf structures in this sense.
So this paper of Aguiar and Ardila about the generalized permutahedra and the corresponding Hopf algebras that go with it. Well, I think it's something to look at.
So the statement, the statement about the normal fan you just saw is still some kind of generalized permutahedron in this case. So you still get the normal fan of the brick polyhedron by removing hyperplanes, defining hyperplanes of the permutahedron, or you get the brick polyhedron by removing hyperplanes, but I'm not very familiar with the algebraic correspondence in this case. But yes, I should look into this picture, into this paper.
Let's thank the speaker again.
Thank you very much.
So